In section 9.1, we took a lot of time to set up the theory behind confidence intervals. We don't know the population parameter, so we use a sample statistic to estimate where the population parameter is. We take the point estimate plus or minus the margin of error. We learned how to find the margin of error. We learned how to find the confidence interval using our calculator. We learned how to calculate z-scores for critical values in order to create the margin of error using the formula, and a whole bunch of other stuff besides. Now we want to use those same ideas, but we want to do it for a population mean. We want to create a confidence interval estimate for a population mean mu, just like we did for proportions in section 9.1. But there's a big problem. So in section 8.1, we learned that X bar has a distribution with center mean equal to mu, if you recall, and standard error sigma of p hat, that'll be your spread, equal to sigma over the square root of n. It's been a while, I know, but that was what we learned in section 8.1. Now we can use X bar to estimate mu as we do above. I mean, we do that all the time. So we say, you know, X bar is close to mu. But what will we use to estimate sigma? Well, we would use S, right? S would be the closest thing we could get to sigma. But hold on, there's a problem with that. Using anything other than sigma will fundamentally change the shape of this distribution. If we do this, if we use S instead of sigma, then this distribution will not be normal anymore. Changing mu to X bar doesn't really change anything, but changing sigma to S really fundamentally changes the shape of this distribution. And that means that if I use the normal distribution, everything's going to be incorrect. All of it will be wrong. Not by much, by a little bit. What I'm saying here is if you use z alpha over 2 like we did in section 9.1, if you'll recall, let me bring up the formula right here. In section 9.1, we learned this formula. You can see the z alpha over 2 in there. Okay, well, we can get away with that because this was based off of the binomial distribution, and therefore the sigma p hat is roughly equal to the square root of the p times 1 minus p over n. This is basically your standard error. Now you can do that because it's proportions, it's built off of a binomial probability distribution, but we're not going to be in so much luck when we're talking about X bar and mu. So we're not going to be able to use Z like we did in the last section. Everything we do, if we do that, will be wrong. Now, what are we going to do? Who's going to find the answer? And the answer is a guy that worked at the Guinness Brewery in Dublin. That's right, Guinness. Guinness is it's famous for making a stout beer. Stout is very, very dark with a lot of foam at the top. Best come out of a barrel. And he was monitoring the brewing process. If you know anything about beer, wine, food in general, actually, it doesn't have to be alcohol, but food, alcohol's long been notorious for this. They want to be very, very careful about the mix when they put the mash in, when they do the fermenting. It's very much involved in chemistry. And a lot of these companies from a very long time have employed chemists, mathematicians, food scientists to develop their formulas, try to keep things consistent. For example, Guinness would like a barrel of stout in Dublin to taste more or less the same as a barrel of stout in Cork, for example, another town in Ireland. So they want them to be consistent, and they would hire people to do this. Companies do this all the time. Pick your favorite chain restaurant. They always do this. They have people who are hired to make the food be very consistent from barrel to barrel, batch to batch, and so on. All right, so what he did was he was figuring out that every time he was making a confidence interval for the mean, like he wanted to know the mean alcohol content of, a beaker, or he wanted to know a beaker full of stout, or he wanted to know the mean, bitterness or whatever in a particular batch of liquor, or batch of beer, I should say, then he was always a little bit off. And being a little bit off doesn't seem like a big deal, but it is a big deal when you're dealing with huge quantities, huge batches, like you would be for a big brewery like Guinness. So what he devised was something called the T statistic. It's a way to cheaply monitor the quality of the stout. So it wasn't going to have the errors that using the Z alpha over 2 would. So he basically made his own statistic called the T statistic, and here it is. And he published it in 1908. Now he hid his name under the name student, quote unquote, because he wanted to hide who he was, because he didn't want Guinness, the company, to know that he was letting out this information because they could fire him for releasing trade secrets. They were trying to hide the fact that they were using chemists to try to make their beer as best, or their stout, as great as it could be. So he hid his name and then released his papers to a friend, kind of acquaintance of his, named Carl Pearson. He's the same Carl Pearson who I should say, developed and discussed the value of R, the correlation coefficient that we learned in Chapter 4. So Biometrico was this journal that Pearson ran, and Gossett got a hold of him and sent him his papers kind of on the down low and said, hey, here's this great thing, but I can't publish this under my name. Call me student. And Pearson said, sure, I'll call you student and I will publish. And he did. And this revolutionized confidence intervals all across the globe, because any place that a mathematician or a statistician was working for a company, they were always going to be a little bit off, and it was driving a lot of these companies crazy. And so he was able to publish the t-distribution and thereby make it so that people wouldn't be wrong anymore. Now, the interpretation of the t-score is very, very similar to the interpretation of the z-score. It's basically the number of standard errors you are from your population mean, or x-bar, I shouldn't say you are. X-bar is from the population mean. So it's very, very, very similar. Oops, I brought that up. The degrees of freedom, DF, often abbreviated that way. Now, I can get into DF in a lot of different ways, but one of the ways for you to realize is that the formula is using S here. And since it uses S, it pays to remember the formula for the sample standard deviation from way back in section 3.2. That is that S is equal to the square root of all this stuff divided by n minus 1. See the n minus 1 down there? That's where your degrees of freedom is coming from. And there's a whole big proof for why this works that I obviously am not going to show in this course, but it exists. You can go search it out if you so desire. But that makes it so your degrees of freedom is your sample size, take away 1. One of the easiest formulas you'll ever have in this course. All right, now let's talk about this t-distribution. So I want us to look at Minitab's results. Minitab, it's a computer program, and I made it do 1,500 samples, simple random samples, a size 5 from the z distribution. So that's the normal distribution, and this is what it looks like. And then I had it do 1,500 samples from a size n equals 5 and n equals 10 from the t distribution. So here's a t distribution with n equals 5, and here's a t distribution with n equals 10. And we want to kind of look at the differences and compare and contrast what we see going on here. So I have to add in a column over here so I can write. So 1 second. All right, now let's start by comparing the z and the t distribution. So the z, remember, is the normal distribution. That's the one that's up at the top. So when we compare them, we want to look for things that are similar between the 3 curves. So what do they all have in common? Well, they all have a center of 0. Look at them, right? So all the curves have a center at mu equals 0. Okay, so they are all centered around 0. Oop, that was a mistake. What else? They're all symmetric. So they're all symmetric and bell-shaped, more or less, right? All symmetric around mu equals 0. So they all have that same center, and they're all symmetric around that center. They all have similar shapes. Now, they're not exactly the same, but they're similar. They're all kind of bell-shaped, right? Now, the true normal bell shape is the one that's up at the top, right? So the z curve is the one that's actually bell-shaped, or z distribution is quote-unquote normal. The others are not normal. They're just kind of a similar shape to normal, but they're not actually normal itself. Normal is very specific. Okay. All right, now let's contrast them. What do they have that's different about them? Z and T distributions. Well, the big difference is spread. So you can see that the Z distribution has the least amount of spread. So the Z curve, Z distribution, has the least amount of spread. remember that we actually know what the spread is. Sigma is equal to 1 for that distribution, right? Oops, and there we have, okay, sorry. Since sigma is equal to 1, remember that we had sample sizes of 5 here. So you can see n equals 5. So that means that standard error of x bar is equal to sigma over the square root of n, so 1 over the square root of 5, which would be about 0.447. And I can just get that with a calculator. 1 divided by the square root of 5, 0.447. 2. Okay, so I actually know how much spread that curve has. It's not very much. So the inflection point, if you will, the standard error, the first standard error falls at about 0.447. So it's pretty small. The T curves are more spread out. Now, how can you spot it? Well, look just at these two. See how the Z curve has nobody at 5 and 6? Look at that. There's no bars there. Whereas the T curve here has some bars there. I mean, it's not a lot, but it has a little bit. It's more spread out. So the T curves are both more, T distributions, you can call them curves, it doesn't matter, are both more spread out than the Z distribution. Now, how can you spot that? They have fatter tails, right? Fatter / larger tails, right? That's the 5 and 6 business. How this curve right here has a 5 and a 6 there, and this Z curve doesn't have anybody at 5 and 6. And they also have a shorter peak. You can see this peak happens at about 0.42 or so. This one, look at that. It's not even up to 0.4. So it's going to have a shorter peak at the center. All right, then look at compare the two T distributions. As n increases, now let's look at this. This one is n equals 5. The one below it is n equals 10. So as n increases, which means, by the way, your degrees of freedom is increasing, what happens? The curve, this bottom one, looks closer to the normal curve than the first one did. Becomes more like the normal distribution. In other words, oops, there we go. In other words, n equals 10 is closer to the normal distribution than when n equals 5. It'll have smaller tails and a taller peak. And you can see that, look at 5 and 6. So over here at 5 and 6, you don't have very many. You still have a little bit. It's not the Z distribution. Z distribution has nobody over there. Look at that. So it's getting closer to that Z distribution. It's not perfect. And the larger your n gets, the more this becomes like the normal distribution. And we'll just have to stop right there, and we'll pick right back up at looking at the T distribution in the next video.